Okay, so this is our first lesson, our first video for the first lesson of the first unit of pre-calculus. So this particular unit, we're going to be working with functions. A lot is going to be just a review, but there are other things that we will cover in this unit that are going to be new. Unit 1 is on functions. First lesson is going to be characteristics of functions. We'll be looking at how do functions behave, what is significant about a function's graph, what makes a function a function. Lesson 2, we'll look at composite functions. Unit 3, or lesson 3, we'll look at one-to-one functions and inverse functions. And then Unit 1, lesson 4, we'll look at transformations of functions. We will have a lesson 5 and perhaps a lesson 6 in Unit 1, but we'll talk about those a little bit later. So let's get started. All right, so the goal here of this lesson is to describe functions numerically, algebraically, verbally, and visually. Before we can talk about functions, we have to talk about a relation. A relation is a mapping or a pairing of input values with output values. Here we've got 3 examples of a set of input values and their output values. So you'll notice in example 1 that we have a set of input values such as 1, 2, 3, 4. They are paired with specific output values, such as 1 is paired with 2, 2 is paired with 4, 3 is paired with 4, and 4 is paired with 5. And you'll see that with the other examples as well. When we talk about relations, oftentimes we talk in terms of domain and range. So the domain is always going to be the set of input values, and the domain for this particular set or relation is simply the set of numbers including 1, 2, 3, and 4. Okay, the range of a relation is the set of output values. So your set of output values for this relation is 2, 4, and 5. So with a relation, you can always identify the domain for a relation and the range for a relation. So let's go ahead and look at example 2. Example 2, 1 is paired with 5. 1 is also paired with 9. You'll also see that 2 is paired with 7, 3 is paired with 7, and 4 is paired with 9. So the domain for this relation is going to include numbers 1, 2, 3, and 4, and its range will be the set of numbers 5, 7, and 9. And then but then we have example 3, where I got real creative and used the same values for the input values for the domain, 1, 2, 3, and 4. And the range for this includes the only value of 7. Okay, so a relation is simply a set of input values paired with a set of output values. Now, let's talk about, before we talk about a function, a relation can also be in the form of a set of ordered pairs. So I can take this input-output data and write this information in the form of a set of ordered pairs. So what would that look like? All right, so you put your 1, which is paired with 2. That as an ordered pair would be 1, 2. Then the input value of 2 is paired with 4. So we would have 2, 4. 3 is paired with 4. So 3, 4. And then 4 is paired with 5. So we would have 4, 5, and that would consist of the relation written as the set of ordered pairs. Now, if you look at this, you'll notice that hopefully you recognize this as a set of ordered pairs, of course, but what do we always associate with a set of ordered pairs or an ordered pair? We always associate an X and a Y. So if all of these represent X's and Y's, then what we can say is that our input values are the set of X's and our output values are the set of Y's. Okay, so for the next example, or example 2, if we want to write those as a set of ordered pairs, then that would be 1, 5. Now notice that 1 is also paired with 9, so I would have an ordered pair 1, 9. Then I have 2, 2, 7, 2, 7 would be an ordered pair. 3, 7 would be an ordered pair. And also, or our last one would be 4, 9 as an ordered pair. All right, and then finally, the last set here, this example 3, as a set of ordered pairs, we have a little bracket, which is kind of sad. But as ordered pairs, we would have 1, 7, 2, 7, 3, 7, and 4, 7. All right, so that just kind of recaps what we know about relations. So now let's talk about a function. A function is a rule that establishes a relationship between input values and output values of a relation. So it's the word, a function is a rule that basically establishes a relationship, okay, hence relation. So there is exactly, for a function, for each input, there is exactly one output. So let me say that again. In a nutshell, a relation is also a function if each input has exactly one output. All right, so let's go back to our 3 examples here. Does this relation in example 1 represent a function? So the question is each input paired with exactly one output? And you'll notice in the table or the mapping, 1 is paired only with 2, 2 is paired only with 4, 3 is paired only with 4, and 4 is paired with 5. So yes, example 1, the relation example 1 does represent a function. And again, it's because each X has its own, or not its own, but each X has exactly one Y value. Okay, well, what about the example 2? In example 2, is there an X value that is paired with more than one Y value? So if you go to your mapping, you'll notice that 1 is paired with 5 and 1 is paired with 9. If you look at your table, or not your table, but if you look at your set of ordered pairs, you'll see here that 1 is paired with 5 and 1 is paired with 9. So no, the relation in example 2 does not represent a function. And then let's go to example 3. Example 3, notice that each X value is paired with exactly one Y value. So the answer to this is yes, this does represent a function. Now, notice that each X is paired with 7. It's okay that 7 is paired with each X. It's just that you cannot have an X value paired with more than one Y value. So, yes, example 3 does represent a function. All right, so now we're going to talk about, there's 4 different ways, or 4 ways that we typically describe a function. One is numerically, which is kind of what we just talked about, using input-output tables or a set of ordered pair. Algebraically, we would work with a function in the form of an equation. We can also describe a function verbally in words. We can also describe a function visually in the form of a graph. All right, so let's kind of revisit the idea of a numerical description of a function. So here we have a table of values. You have an input table, you have a set of input values, you have a set of output values. The question is, does this table of values, does this relation represent a function? And the question is each x paired with exactly one y? And the answer is yes. All right, then what about this example? This example, we have another table of values. 1 is paired with 5, 2 is paired with -1, -3 is paired with 6. So yes, this also represents a function. And then for the third example here, 1 is paired with 1, 2 is paired with 4, 3 is paired with 9, 4 is paired with 16. So yes, again, this example also does represent a function. So this is a table of values, and each of them do represent functions. If we go back to what the definition of a function is, and we look at it as a rule that establishes a relationship between input values and output values, if we go back and if we look at these three examples, even though all three of these do represent functions, there's only one that I think you can actually determine what the relationship actually is between the input values and the output values. So if we look at this, each output value, 1, 4, 7, or not 7, but 1, 4, 9, and 16, these are the result of squaring the input values. So this relationship can be written in the form of an equation such as f or y equals, the y values are obtained by taking the x value and squaring it. So when x is 1 and you square 1, you get 1. When x is 2, you square it, you get 4. 3 squared is 9. 4 squared, 16, and we could continue additional values in the table if we wanted to. But a function is a rule that establishes a relationship between input values and output values. And sometimes the rule is obvious, and sometimes the rule is not. We don't know exactly what the relationship is between the x values and the y values. Okay? All right, so now let's talk about a visual description of a function. So I'm going to go to page 2 of your notes, and I'm going to bring this down. So here we have, I've got 5 graphs, and I want us to determine if these 5 graphs represent functions. And I'm hoping that when you look at the example here, this first example, that looks like a parabola opening to the right. I'm hoping that you realize that no, this does not represent a function. No. How about this example here? Well, this is an absolute value function, and this function, or this graph, does represent a function. This graph does represent a function. Now this particular graph, this graph is a vertical line. This is not a function, and this horizontal line is a function. Now I'm hoping that you are you remember what I'm thinking in terms of when determining if these are in fact functions. And what was I using? I was using the vertical line test. So if you picture a vertical line, remember vertical lines are vertical, up and down, if I can get this situated. If you picture this pencil as a vertical line, how many times does the graph intersect this vertical line? And the answer to that is twice. So if a graph intersects the vertical line in more than one place, no, it is not a function. So vertical line test, this fails the vertical line test, so no, it's not a function. This particular graph passes the vertical line test, so yes, it is a function. This graph passes the vertical line test, it is a function. A vertical line intersects a vertical line in all places, so no, it's not a function. And a horizontal line test does pass the vertical line test. So there is the recap of the vertical line test. Now, before we kind of move on, let me just kind of remind you what the significance behind the vertical line test is. A vertical line is a visual that identifies points of a graph that have the same x value. Now, this value is, I know that value is negative, the x value is -2, but that point is like -2, I'm going to say it's 2.5, the y value. So -2, 2.5. This point is -2, -2.5. So if you notice, these 2 points right here have the same x value. So therefore, this does not represent a function. Okay? All right. Now let's talk about an algebraic description of a function. So an algebraic description of a function is in the form of an equation. So let's think about this. If y equals 2x minus 3, by the way, can you recall what that graph would be? F of x, or if y equals 2x minus 3, that is a line. Hopefully you guys remember it to look like this: a y-intercept at -3, the slope is 2, the graph would look something like this. So the question is, and this does represent a function. The graph passes the vertical line test, so it's a function. Since this is a function, y equals 2x minus 3, then because this is a function, we can use function notation. And the function notation would be f of x equals 2x minus 3. So since this graph represents a function, we can write it not only as y equals 2x minus 3, but f of x equals 2x minus 3. So if y equals 2x minus 3 and f of x equals 2x minus 3, then y must equal f of x. So y equals f of x is simply f of x is simply another way of describing y. So f of x represents y values. So when a relation represents a function, the function can be used can be written or described using function notation, which is what we have right here. Okay? So the key here is just remember that f of x is just a fancy way of writing y. So this any ordered pair on a function, you have, we usually like to write it as x comma y, but a point on a function can also be written as x comma f of x. Okay, so x comma f of x is the same thing as x comma y. All right, so the cool thing or the nice thing about functions when they are written or described in the form of an equation or in function notation, then evaluating a function is pretty simple, pretty quick, pretty easy. So how do you evaluate a function, f of x equals x squared minus 3x plus 4, for the x values of 0, 2, -1, and 3? Okay, all that's saying is if our x values are 0, 2, -1, and 3, what are their corresponding y values? And to find that, all we have to do is substitute. I'm going to start with 0. I'm going to substitute 0 everywhere I have an x. So I will start by substituting 0. F of 0, the function evaluated at 0, is equal to 0 squared minus 3 times 0 plus 4. And when you clean all of that up, 0 squared is 0, minus 0, and then plus 4. And what we can do now is we can actually write this ordered pair, or write the value here, or the result, as an ordered pair. So when x is 0, the y value of this function is 4. All right, and we can do that for the other values as well. If I want to evaluate the function at 2, I'm just going to go ahead and set this up. And f of, okay, just, all right, so now I'm going to go in. All right, let's go with 2. So the function evaluated at 2 will equal 2 squared, which is 4, minus 6, that'll be -2, and -2 plus 4 is 2. So as an ordered pair, that would be our x value of 2, the y value of 2, so the ordered pair is 2, 2. And this, I'll put this in pink also. Okay, then their next value is -1. Substituting -1, I get -1 squared, which is +1. This -3 times -1 is 3, so 1 plus 3 is 4, 4 plus 4 is 8, so our ordered pair would be, hang on, let's use this, it's supposed to be an erasable pen, but anyway, I'll just scribble over it. So let's rewrite that. My ordered pair is -1, 8. And then finally, substituting 3, I get 3 squared is 9, minus 9 is 0, and then the result is 4. So ordered pair would be 3, 4. All right, so evaluating functions is simply just plugging in our x values and then simplifying the expression, and we can always take those values and write them as ordered pairs. Okay, so, all right, I'm going to finish out this portion of the notes, or this, I'm gonna finish out this video with this example. And sometimes when you want to create, or when you want to evaluate a function for a variety of numbers or multiple x values, oftentimes creating a table is helpful. And in Algebra 1, or maybe even pre-algebra, you guys probably learned or worked with simply creating a t-table. I'll use it up, I'll kind of draw it up here, like where you would have your x value and your y value. Well, for calculus purposes, I like to create a 4-column table. And so when I show, I'm going to go ahead and substitute. If this is just an organizational tool. So I'm going to substitute 0. And the x squared minus 3 is the function, which I kind of left that off right there. Should have put f of x. That should be f of x equals x squared minus 3. So now I'm going to show right here, this is where I'm going to show substituting my x value. My result is -3, so that's my f of -3 value. And then as an ordered pair, 0, -3. And I'm going to do that for all of these points. So I'll start with 1, or I'll continue with 1, and that's 1 squared minus 3, which gives us -2. The ordered pair would be 1, -2. I'll then move on to 2, and when I substitute 2, I end up with 1. So my ordered pair is 2, 1. And hopefully this is just kind of reviewing some things that you did from Algebra 1 and Algebra 2. I will now substitute -1, or well, I skipped 3, but I'm just going to go ahead and do -1. Here's where you have to be careful when substituting negative numbers. It is very important that you substitute your -1 and put it in parentheses, because this expression says that you are squaring whatever x is. And if x is -1, you want to square the -1, which gives you +1. When you subtract 3, you get your -2, and your ordered pair then would be -1, -2. And then I'll do -2, same thing, parentheses, very important. So you'll square the -2, which makes it +4, subtract 3, you get 1, as an ordered pair, -2, +1. And since I kind of ignored 3 a minute ago, I'll come back down here and put 3 in. So substituting 3, that will give me 3 squared is 9. 9 minus 3 is 6. So that would be 3, 6. And I'll do -3. And we get +6 again. So our ordered pair is -3, 6. So now now what I want us to do is I want us to plot these points. And now all I have to do is just kind of look at my XY column, and I will plot my points, and let's see what I get here. This grid is a little small, so I apologize, but 0, -3 is here. 1, -2 is here. 2, -1, nope, 2, -1 is here. That's not right. It's 2, +1. So I knew something didn't look quite right. So I'll go over, that's 1, there's 2, 2, 1. And then I have -1, -2. I have -2, +1. And then I have 3, 6, over 3, up 6, which is going to be up here. And -3, 6. Now, I'm hoping that you recognize this as a quadratic. So when you connect your points, don't make it into a V shape, because quadratics are not V-shaped. They have a curve. They have the shape of a parabola. Now, I'm putting arrows at the ends. The arrows indicate that this graph, this function, continues and does not just include the 1, 2, 3, 4, 5, 6, 7 points that I've included. This quadratic, this parabola, includes all of the numbers and all of the points, rather, that are on this graph, okay, including the ones that would go on infinitely. All right, so that concludes this portion of the lesson. This is going to conclude part 1 of lesson 1.